Thanks, Chester, for the nice introduction. Thanks for inviting me to give this talk. Yeah, from the pre-talk games, I saw it's a large audience, a lot of people, a great audience. So very glad to give this talk. So I'm a little bit under the weather today, actually. So if you hear me cough or you hear me voice broken during the talk, apologize in advance. And today I will talk about a topic that I'm very interested in, and we did some work. It's just the beginning, I will see, and definitely a lot of work still to be done. The topic is federated learning with public and private data from small models to large and back. So probably a lot of people know federated learning. If you don't know it already, the concept of federated learning is the motivation start from privacy regulation and the privacy preserving methods for training user data for these machine learning models. And in federated learning, a large set of clients can collaboratively learn a model without transferring or exchanging their data. Instead, they will change intermediate results and only necessary information for a model to be trained. And we will talk a little bit more about it later. And during this talk, we will heavily focus on the origin motivation of federated learning, where the clients are mobile devices, and after we learn a model, the model will also deployed on mobile devices. This is what we often call cross-device federated learning setting. Although it's what I talk about mostly applies to cross-device federated learning, the principles and the research insights can be more widely adopted by, let's see, federated learning in a setting where we need efficient client resources. It's probably even true for today, for if we have GPUs or desktops or desktop workstations as client devices, but we train very large models, which can hard to fit on a single client. And many institutions that have their own data that they don't want to exchange with each other and want to learn a model that performs well with privacy preserving methods. So I will talk a little bit about the practice or what happened in federated learning now in the angle of the spectrum of model sizes from small to large. Let's see, what we often talk about, at least for Google and a lot of the companies do cross-device federated learning, is for a machine learning model smaller than has just smaller than 10 million parameter size. It's already widely used in production. And the recent progress is in more on the advanced privacy techniques. So on the right-hand side, I show some example papers I am deeply involved in, which I will talk about in a little bit more detail in the later part of this talk. This including applying differential privacy techniques in addition to federated learning for these models in both novel research techniques as well as in the real production setting. And growing the model to be a little bit larger, if we have 10 million to 10 billion parameter size, this is a large range, I realize that. So all these models can be possibly put on mobile devices for inference, which also means that there's a potential for doing training, parameter efficient training for these models. There are a lot of research on models at this size, and also some early exploration, though we don't know, at least for the cross-device federated cross-device setting, we don't know, there's we are unaware of a production deployment that has been announced at this level. So this is a part that I'm very interested, but I won't spend too much time talking about it today, but we have some interesting research work. These are the 2 papers I contributed to, and just some examples of what research can be like in this regime. And another, like, if we grow to even bigger, this is like today, a lot of people are interested in these very large models that have more than 10 billion parameters, which are believed to show emergent abilities. A lot of impressive applications of generative AI by these large language models or large multimodal models. There's a big question mark on what happens for these large language models when they interact with like mobile devices. So we will touch a little bit today, but probably not in a conventional cross-device federated training of these large models way. So we view this in another angle of like the emergent needs in both academic research and like real production applications in industry, is that there's a view of public and private data. Like data is of course very important for the like progress in machine learning in recent years. Start from like the like ImageNet uh, like collected large scale data sets in the past, large scale data sets that drive the deep learning to like the various web data that are used to train large language models and the large multimodal data. On the other hand, like people see that at some point all this public data might be exhausted, and also for a lot of the applications, private data are very important, has much higher quality than this noisy web data. What we can do, what are the interesting things we can do with respect to, we have public data, both public data and private data in play, and we are very interested in use this high quality private data in a privacy preserving way. So I will start from the small model where we have a lot of production development, and particularly talk about our recent like progress in applying differential privacy. In addition, in the federated learning setting, for this 10 million 10 million machine learning models on mobile devices. And at this regime, we have a lot of applications at Google that use federated learning and a closely related technique, which we call federated analytics. Unlike learning, where we learn a model, the model is not necessarily very large, but 10 million is also like, compared to like a linear model or some statistics like histogram, is also a reasonably large scale. Federated analytics will use privacy preserving methods to collect some important statistics, again, share the same spirit as federated learning without transferring users' data without collecting users' data. The application at Google, including like smart text selection, a lot of Gboard applications, Google Health Studies, and the Hey Google hardware detection for the assistant applications. So we will talk a little bit more about the Gboard applications in the following part of this talk. Like the small on-device language models powering a lot of applications in Gboard, including next word prediction, smart selection, smart completion, smart compose, all that. Because these are on-device models, they are relatively small compared to what we commonly talk about language model today. They are like one layer LSTM model or variant of LSTM called CIFG. And the model size is somewhere between 2 million and 8 million parameters. The main difference for these models are like the vocabulary size. So before I talk about the techniques we use for differential privacy and our progress in differential privacy in federated learning practice, I want to mention about the privacy principles in Gboard, like the privacy principles we generally considered and how these principles are reflected in the Gboard production. So privacy is not like a binary concept. It's multifaceted, and there are many aspects of privacy. This including transparency and user control, data minimization, data anonymization, auditability, and verifiability. For user control, what we have for Gboard is like user can easily configure that so that to choose whether they want to participate in learning or not. They have full control of whether they will participate in learning or not. And for data minimization, we heavily rely on federated learning techniques where the data are never transferred from clients to the server. We never collect this data. And we further apply encryption methods like secure aggregation to have a guarantee that only aggregated results from multiple users of the ephemeral updates can be accessed by the server. And for data anonymization, which we will talk a little bit more later, is we heavily rely on differential privacy techniques. And we have open source code and all that, and we are actively working on improving our next generation of the system to provide stronger verifiability for third party to audit what we have been doing. For now, our main technique for this is still to fully disclose what we're doing, give all the information as much as possible, including papers, open source code, and all that. So we will talk a little bit more about data anonymization. For data anonymization, we want the trained model to not memorize individual users' information. So we heavily relies on the concept of differential privacy, and more specifically, we use a user level differential privacy. For level differential privacy, what we mean is like consider the neighboring data set defined on users, which means that if we change the data of one user in the entire population, if we train models on these two neighboring data sets, the output distribution of this algorithm won't change much. They are very close to each other, almost identical to each other, which means that without that specific user, it does not change the learning behavior. So by doing that, we can guarantee that the trained model won't memorize each individual user's information. And after training with differential privacy, again, it's will deployed on mobile devices. Like the DP guarantee in this process apply to all the intermediate results, which is particularly useful for federated learning because even the intermediate global model will be transferred, downloaded by a small set of users to perform model updates. So although theoretically we don't have that, but empirically we have shown that by some empirical auditing method that the final model checkpoints, if we not giving the access to the intermediate models, have a much stronger privacy protection effect on the model on the training data. So here I show the system we use. Can be a complicated system. Let's walk through it step by step. Like the black word and the process there is basically what we have for cross-device federated learning. A training round usually starts with like a global model broadcast to clients. And each client performs some local updates, usually with their local private data and the model we get, the initial model we get from the server. And the local optimizer usually is just SGD to save the computation and the memory budget on mobile devices. After several steps of training, we will send back the aggregated model updates from multiple iterations on all the private data, and potentially the a big chunk of the private data they have. Each client will send back their updates for this round, and the update will aggregate it across multiple devices, and then this aggregated update will be used to update the global model. Then at this point, the aggregated update is used kind of like a pseudo gradient, and you can use many advanced optimizers as you want, like SGD with momentum or adaptive optimizers. And particularly for adding differential privacy, now you can look at the blue words now. For adding differential privacy, the main technique we do is that we like control the contribution of each device by clipping the updates they send back from mobile devices to the server. And then after aggregate the results, we will add some noise to get a formal differential privacy guarantee. This is a main thing we get. And after that, the gradients are already anonymized in a DP sense. Then we can release and safely use it to update the model. This anonymized updates has the privacy preserving nature, won't leak any of users' information. We do it many rounds, then eventually we release the model. And secure aggregation happens at aggregating the results. Note that all the differential privacy guarantee we mentioned here means a central DP guarantee. It's used for prevents the model from memorizing user data. And if you look at those highlight parts, these are something considered fairly new for us to get a strong DP guarantees. And for us to get these formal DP guarantees in practice, what we do with like public pre-training, pre-training on public data. And in order to get formal privacy guarantees, we have a mechanism to control the client participation. We control the total number of participation a client can have for the total in the entire training process in multiple rounds. Also, we control the frequency and have what we call minimum separation of two clients between between two participation of a specific client. Another important part, algorithm innovation we have for us to get these DP guarantees in practice, particularly for this cross-device federated learning setting, is this new line of algorithm we call DP-FTIL, which adds stateful noise. This is the first version is developed in our ICML 2021 paper. Then we talk a lot about how we apply this technique in practice to get the results I will show very soon. So let me talk a little bit.
Sorry. Before you move on, there's a couple of questions I want to interrupt you there.
Sure.
I think the one question is related to talk about your clipping, and the question is what do you mean by clipping after training? So once you use the user's data to train the model, you clip out the user's input so the model doesn't memorize it. So maybe you can just explain that. Or there's a related question. Is the clipping going to impact the learning as well? How do you balance the learning and the privacy? So I think that's a clipping related question.
So basically, we consider, let's see, this is based on a federated averaging algorithm framework. The client will send model updates back to the server. What we mean clipping is to control the L2 norm of these updates. So that's a common way to do clipping.
The other questions, okay. The other questions, I think, are just general questions. Say basically, you train the federal learning models, and how do you make the model specific to clients? I think that's what the question about. So can you speak more on this? Focus only on updating, helping improve a specific model. How does that work?
this talk will not touch that part. We have a lot of research and also some usage of what we often call personalization in federated learning. Like a very simple solution that if you have a global model, you fine tune based on your private data, a few steps, or incorporate the user history when you apply these models can often work very effectively.
Okay, so there's one more question, probably you can leave to the end, but basically asking why you're using TensorFlow, not PyTorch.
Yeah. So I guess it's still valid that TensorFlow support on-device deployment and engineering efforts very well. That's in addition to we are Google. So, okay, I'll continue. So I'll probably skip due to limited time. This is like a short history. We use federated learning to train these models for years. Like there's a strong commitment. All these models are trained with federated learning, and we never collect all the user data. In 2022, we have the first production neural network. As far as we know, this is the first production neural network trained directly on user data announced with DP. Then we get all these network prediction models with DP. And another thing I want to mention is that in 2024, our recent advances, like we get some of the models with very strong DP guarantees of epsilon smaller than 1. So how did we get there? Let's go back to this figure again, this complicated figure, but of the system, but we don't need to go through it again, as we are somewhat already familiar with it. There's no magic there, what we use. We only get these very strong DP guarantees for some of the models. Some of the models when we have a large population of client devices, and we stress the system to use a larger subset of clients every round. And of course, there's some novelty, some innovation we made on the algorithm side. This is a new paper, the NeurIPS 2023 paper we have, that improved the previous DPFTL algorithm, the first version with tree aggregation for DP prefix sum. Now we extended to use a matrix factorization mechanism, which is much more stronger, powerful, and more customizable. But having all this together, we get we can train production models with even stronger DP guarantees. Now I want to show you a little bit of the results. So this is an application in the production Gboard language models. We always talk about privacy utility trade-off when we have these privacy preserving methods. We see the potential of utility improvement from this high quality private data. But the more privacy preserving techniques we use, it's potentially that we will have some privacy drop, because part of the model performance potentially relies on memorization, though it's not necessarily true in a lot of cases. So when we talk about utility for all these production use cases, applications, we will always measure them by strong utility in A/B testing. Compared to a previous n-gram model, it's a relative weak baseline. We will always aim for better utility, better usage of users of these models. And compared with a previous neural network model without DP guarantees, this is considered a very strong baseline. We will aim for comparable utility, but now the model has a very strong DP guarantee, much strong with advanced privacy preserving techniques. As I mentioned before, one key thing for us to get good privacy and utility at the same time is that in practice we do some trade-off. We use a lot of computation we use two sightings. One sighting is 6,500 clients per round. Another is 12,000 clients per round. Those are much larger than what commonly used in practice before and what often reported in research papers for cross-device federated learning. So let's look at another dimension. We talk about privacy and utility. Now let's look at privacy. Our privacy measurement is the DP guarantee, the value of epsilon when we have a very small delta 10 to the negative 10. And for epsilon, the smaller the better. The smaller means stronger DP guarantees. And epsilon equals to 10 is considered a reasonable DP guarantee, a tier 2 DP guarantee for these machine learning models. It's a very hard task if you are familiar with the literature of differential privacy. And epsilon equals to 1 is very strong DP guarantees, even in from the point of view of a theorist, this is a very good DP guarantee. So the x-axis of this is the various network prediction models we trained, and we train different models for different language locale combination. And the first model we launched is this ES-ES model. It got DP guarantee of, let's just look at epsilon for now, is 8.9. And smaller is is already like falls under the tier 2 the protection. And then we apply similar techniques with some improvement like public pre-training. We train DP models for all these different models for Gboard network prediction. If you look at the Spanish model, the ES-ES model, by the techniques we have, we improved the DP guarantee from about 9 to about 6. And then we use matrix factorization mechanism for the Spanish language model, the ES-ES model, by just replacing the old DPFTL algorithm with this matrix factorization version, we further improve epsilon to 3.4 also. And if for some larger populations, let's see the Spanish model in the combined population of Latin America and the PT language in Brazil, we can get epsilon smaller than 1. So I will end this part with the announcement we have in a fairly recent blog post. As of today, all network prediction neural network language models in Gboard are trained with federated learning with formal DP guarantees, and all future launches of Gboard language models trained on user data require DP. The 30+ Gboard on-device language models are launched in 7+ languages and 15+ countries, and satisfy epsilon delta DP guarantees of delta, small delta, and epsilon between 0.994 and 13.96. To the best of our knowledge, this is the largest known deployment of user-level DP in production at Google or anywhere, and the first time a strong DP guarantee of epsilon smaller than 1 is announced for models trained directly on user data. So let's go back to, let's see what do we have for slightly larger models. I only have a few minutes left, so I will do it fairly quick. Again, from the view of public and private data, I will mention 2 works. One is can public large language models help private cross-device federated learning? Another is a recent one we put on archive, prompt public large language models to synthesize data for private on-device applications. So this is a paper a previous intern did with me. A lot of the work is still in a simulation setting, unlike in a previous production setting. But we heavily consider the realistic constraints we have for real-world deployment. We like I mentioned, we already use public pre-training for production language models. But this is at that time, this is still new that we want to explore a little bit. So also some inspirations we get from training larger models with differential privacy, not in the federated learning setting, in research, from some research inspiration. Another thing we did is to explore a little bit about a public tokenizer from large language models, the powerful sentence piece tokenizer. Can we get some help from that? It turns out that it's pretty useful, but again, there are some challenge for using it in the like features in the production features we have in Gboard. we are still investigating that. And another part of the paper is about how we can use these public language models to help the private training, the pipeline I mentioned before, like federated learning with differential privacy. We explore two techniques. One technique is distillation from public large language models. It's probably not too surprising, but what we do is like during the pre-training stage on some of the public data, we use these large language models to do distillation. And another technique we use is to do some data filtering of the public data based on an intermediate checkpoint of the DP model. As I mentioned before, like the DP model, all the intermediate results have DP guarantees. They are considered anonymized and can be used safely. So one important observation from us is that from knowledge distillation, we improved the utility, the final accuracy a little bit, not much. Using private data is still very powerful. After fine-tuning, again and again, we show that after fine-tuning on private data, the performance is strong. But interestingly, if we do distillation and distribution matching, we can significantly reduce the number of public data required to get the similar performance. So I think I'm running out of time. This is a more recent paper we put on arXiv. This is specifically designed to address some of the questions we have in the previous paper. That it's a very good research exploration, but it's relatively hard to use that method in practice for production due to various reasons. The main reason is compatible with current production pipeline. We have to change to WordPress tokenizer. We have to do on-the-fly distillation, and we also have to break the training into two parts to do the distribution matching. Do we have simpler methods? Especially consider that these large language models are shown to have emergent generative ability. What we do here is that let's just try to get better public pre-training data. We use large language models to do with some specifically designed prompt to first filter the C4 language model, and then to generate some synthetic chat data to help the training. So this is what we did for that. In addition to this, like simple ideas, we do extensive experiments in a production setting, where on one hand, we do have a very clear gap between public and private data distribution. One message is that at the beginning of the this curve shows the DPFL fine-tuning on private data on real user data. And we do public pre-training on either the public C4 data set we have been using before or the new data we generated or filtered with large language models. If you look at the curves, the data we get is somewhere in between the old public data and the final model performance after fine-tuned on private data, even closer to the private data. Another message, of course, is that private data are still very high quality and it significantly improved the performance. But the positive side is that even after fine-tuning with the high quality public pre-training data, we still get a little bit of the gain. And the more promising observation is that we can get to a better model performance faster, which gives us some advantages on the DP guarantees we can get, because it means that we use less data and more intuitive, less private data, and more intuitively gives us a better privacy protection.
I think we out of time.
Yeah. So this is what I have talked about. And a big open question is like, what are the future development we can have for private high quality data and large language models? I want to end this talk with the question of what is federated learning? We have some definition in the original paper and the blog post, and later evolved it in 2022, what we need to do to adapt to the new world of model becoming larger and larger, more and more challenges, and the value of data in this new era. I will stop it here. Thanks a lot.
Thank you, Zheng. I'll get 3 questions, so I want you to end because you can get a chance to answer questions. So one question is, what caused the differential privacy score difference between different languages?
So this is a very good question. I think the main reason is the population size, and of course this is a production setting. It's not like we have controlled environment. There are many factors that affect eventually which model we can launch. So as the main reason is population size, but there are also other small factors. And again, we did not heavily do hyperparameter tuning. The main goal is to get a model that works well for our users and with like a strong privacy protection nature.
Okay. Next question is related to, have you tried the inversion attack on these language models or large language models?
Well, what kind of inversion attack? And in old days, before we have formal DP guarantees, we tried some kind of attack called secret sharer. And I'm not sure what the inversion attack means. That usually like the DP community considers reconstruction attack and the member inference attack. And with a DP guarantee as strong as ours, various research paper has shown that there's none of the attacks will be successful. If you are considering like reconstruction from the gradients you client send to server, that's like not what DP is used to tackle. It's more of the job of sector aggregation and the data minimization principle.
Okay, so the Mona also asking, so what's the differences in columns with the epsilon equal to 1 and 18?
Let me. I think it is the same one as the previous question. Why it's different? The main difference is the population size.
You have the 2 columns. I think you passed it. You have 2 columns with the epsilon equal to 1. It's in the later slides. I think you just passed it.
Which one?
No, not this one.
What difference?
The epsilon EPS equal to 1, EPS 18. So I think one of the 2 columns. If you go to next few slides.
This is the last slide for these bars.
No, there's one more. Yeah, I think this one.
This one?
No. You pass it again. Go back. Yeah, this one. You have epsilon to 1, epsilon 18.71. I think in the Mona, that was the Mona's question.
Okay, so this is like a more of a research simulation data set. For this small data set, all this DP has somewhat affects the utility. Epsilon smaller than 1 means that we add more noise, so it affects the performance more. If you compare epsilon, small epsilon and larger epsilon, the small epsilon gets like lower utility or prediction accuracy. I think the main message is to compare for this is to within different epsilon compare the performance of different tokenizer. Like see the sentence piece tokenizer get better performance than the unigram tokenizer.
Okay, the last question. Can you provide more details on how the performance of federal keyboard and language model in A/B testing compares to non-differential privacy and neural models? And how does the number of client devices per round affect the privacy utility trade-off?
For this one, it's like comparable. Usually it means like within like the variance of these metrics, they should be at least as good as. If you are interested in the specific numbers, feel free to check the paper we have at the ACL 2023. we have full disclosure of the metrics we use for these models. And for clients, for the number of computation, this is a kind of the known trick, although I'm not sure if it's widely known before we use it in practice and the recent years development. But this is a trick we have been using many years in our group, is that the potential performance drop from differential privacy is mainly by adding noise. And by having more clients per round, you have more information to be aggregated, then that reduce the noise you added and increase the signal noise ratio you have. So at some point, then we can recover all these utilities. So the concept of differential privacy is basically, let's try to learn the common sense, not the individual information.
Got it. All right. Thank you so much. That's the first talk. Thank you. I know a little bit over time, so let's jump right into the second one. Ziyue is one of the senior researchers at Nvidia. He has been working on federal learning for a while, and he also working for medical imaging and many others. And Ziyue, go ahead.
Sure. Thanks, Chester, and thanks, Zheng, for the informative talk. And in this talk, we'll cover the federal learning, what we can do and what we should consider towards a real-life studies. Hopefully, this talk can provide some information that may help to answer Zheng's last question, what is federated learning? So let's get started. And okay, so yeah, so why do we need federated learning? As we know, people discuss and queries a lot towards different aspects of AI model development, but there is one common consensus that only few people will argue, is that in order to build a robust and generalizable AI model, we mostly gonna rely on the quality and quantity of our data. However, that is also the same reason why such model is hard to build, because there was a lot of data constraints, and especially for the medical applications domain. For example, we have the main reason is data regulations, and maybe at some time it's purely the moving cost of the data movement that restrict the data access and moving around. For example, you have a lot of data that may take months for you to move from one place to another, so that you can collect it in a centralized manner. And another reason is about data availability. For example, in medical domain, we really need experts' knowledge and to collect the data, and the time cost is sometimes unaffordable. And sometimes, for example, in rare disease cases, the data itself is just limited, because that is why it's called rare diseases, right? And beyond that, we have data privacy concerns. Even if we have approval from the data access, we have approval, we have collected the data, but there are still data governance and data privacy concerns. So in order to solve such data limitations, one potential solution, as we're talking about today, is collaborative federated learning. The main idea being that we share the models, not the data. And actually, if we think about it, it's actually the similar idea as distributed learning. But of course, the two terms, federated learning and distributed learning, approaches the question under different problem settings. One is more towards resource utilization, and for the federated learning, it's more about data privacy and transformation restrictions. So three things, what we're gonna consider towards a real-life federated learning study. What are the challenges we face? What the algorithms we're gonna choose? And we need a certain framework for us to perform the real-life studies. The challenges of before we actually perform any federated learning involves like what are the applications, what are the modalities we are using. Is it image, or is it language, or tabular data, or a mixture of different modalities? And second is that how our data distributed. Are we facing a horizontal data distribution, meaning that everybody has the same feature space? It just different parties have access to different populations. Or is our data distribution is vertical, meaning that our samples are distributed across different parties. Every party holds part of the features. A simple example will be financial. Like we all have our data in different financial institutes, banks, borrowers, whatever. But that is for one single sample. Different parties hold different features. So that's in those cases, we're gonna need a slightly different algorithms to handle such data distribution difference. And third one, of course, is the data heterogeneity. As we know, different institutes often faces different populations, and particularly for medical devices scenarios, different imaging devices gonna really produce the data that of different distributions, even if they are the same modality like CT or MR. That's gonna cause client drift, and then further poses significant challenges for the learning process. And finally, is about the security requirements and the communication constraints that usually is a big consideration for federated learning. And as for the algorithms, of course, the very baseline is fed averaging, meaning that the global aggregation is simply by taking the numerical average across different submissions. And here in this talk, I will briefly cover two of our previous researchers, that is considers the different aspects of federated learning, one towards contribution estimation, and the other towards the vertical federated learning. And the final pieces for performing an actual and real-life study is the framework. To perform a real-life study, we need a proper system and infrastructure support that enables us to utilize data security features and inject different algorithms smoothly. And for that, I will introduce the NVFLARE, that is Nvidia Federated Learning environment, our product. So let's first take a look at about the challenges we have. The first one being the application domain. That is really the deterministic factor that's gonna determine which algorithm we're gonna use, and how the data we are gonna face, and what kind of orchestration we need to perform the federated learning process. For example, the healthcare, we're gonna have a medical imaging data that can be big for every sample. And for robotics, we have different challenges, like the data produced in real time, and we have okay computation resources. And of course, we have variables that is more towards the cross-device scenarios. And like some other application domain, like financial or pharmaceutical, energy, automotive, all of them have different data types and data distributions that is gonna determine what kind of algorithms we're gonna use, and what kind of learning process is most effective towards these applications. And based on the application domains, we can have cross-silo or cross-device scenarios, and maybe something in between. With regard to computation resource we have at each participant, and with regard to communication bandwidth limitations, all of them will be taken into consideration for determining what is the best option that we're gonna use for performing such federated learning process. And of course, we have a training data collection and availability difference. Is it statics, meaning that oftentimes we perform some retrospective learning across different parties, or is it the data is collected dynamically as active learning or continuous learning based on some pre-trained model? And but all of them, keep in mind as we talk about federated learning. Federated learning is actually domain agnostic, and so does the federated learning platform. So in the sense, we would like to support the applications in different domains and by using different algorithms. And talk about data modalities and tasks related to different modalities. We can have image, like this segmentation task. We input a 2D MR slice, and hopefully with some deep learning algorithm, it can give us the predictions output of the segmentation mask. And we can have languages, smaller models like BERT on token classification task, and recent large language models, which can be billion level with fine-tuning, either supervised or parameter efficient fine-tuning schemes. And keep in mind, we can have other data modalities like time series, healthcare data like ECG, and we can have tabular data that is commonly utilized in financial sector and also healthcare records. And when it comes to real life study, we can also expect the multimodality data because that is really how our humans make our decisions. Like a doctor's gonna make his or her clinical decisions based on image plus reports plus ECG plus blood test results. All those informations fused in order to reach the final clinical results that will be most robust. And as I mentioned, there will be challenges from data distributions, either whether it's horizontal or vertical, or a mixture of different scenarios. And for that, we're gonna need to choose our learning methods properly, some based on things like self-supervised learning or split learning. Data heterogeneity. I will call data heterogeneity both a curse and also a blessing for federated learning. Why do I say that? Because distribution shifts across different participants. That is main cause of for local learning drifting away from the global model and from each other. And if we have this issue, then when we do the federated averaging or aggregation at the server level, the learning efficiency and effectiveness will be challenged because, every party is pointing the optimization towards different directions. And if we just simply average them together, then the final direction will not be that efficient from the model optimization perspective. But on the other hand, this is exactly why we even need federated learning. Think about if every individual participants, they have the identical distribution, then maybe, well, if one site have sufficient data, then the model generated based on this single site will be able to generate as well for all the other parties because they have the same distribution, right? And the only reason why we even want to perform federated learning is because we want to try our best to cover as much data variability as possible by utilizing the different data distributions across different clients. So there are methods trying to reduce the negative impact from the data heterogeneity. For example, this SM work we proposed back in 2022. And there are some methods trying to utilize the positive aspect of it. For example, this FastDigi work trying to interpolate across different data distributions from different participants. So data heterogeneity also means data variability that we would like to utilize. And if we think about federated learning in a more generalized way, will be collaborative model training. The major advantage here is the decouple the model training from direct access to raw training data. And the simplest form of collaboration will be model ensemble, right? It's just a two-step solution. Clients build models based on their own data, and then a global model can be built as an ensemble of all the local models. But if we have algorithms that involving iterative optimization or model growing, then the collaboration can be performed at finer scales. Taking deep learning with horizontal splits, for example, it's gonna have a pretty clear boundary among these terms. Like stepwise will be distributed learning, but thinking a common deep learning optimization process, we're gonna perform it with several or hundreds of epochs, and every epoch gonna involve hundreds or thousands of steps. So that's gonna be too many steps for federated communication. And that is why for federated learning, usually we formulate it in a epoch-wise collaboration. That is a balance between the stepwise and model-wise. And model-wise, of course, as we just talked about, will be just a simple ensemble. But if we think about this in a more generalized manner, extending to cover other machine learning methods with distinct training schemes and model representations, sometimes these boundaries will become less clear. Really, to formulate a method under a federated learning setting, we need to have answer to these three major questions. The first being, what information should clients share with the server? Is it model or model updates or some intermediate training results? And second one being, how should the server aggregate the collected information from the client? And the third one, the final one, is what should clients do with the global aggregated information received from the server? Once we have the answers to all these questions, then we can properly formulate a particular machine learning method into a federated learning setting. And finally, we have a security and communication.
Before you move to the next session, there are two questions. Just kind of interrupt you. Two questions from the same author. Basically, the asked question is this: in the context of model-wise collaboration, you talk about it, where local models can deviate significantly, what strategy or algorithm do you recommend to effectively ensemble these local models without losing the nuances, patterns that each model may have learned from its unique data sets?
Mm-hmm. Yeah, actually, to counter the negative effect from heterogeneity, we have a set of options. Briefly, I think we can briefly categorize them into three categories. One is to restrict the local optimization directions so that it will not heavily deviate from the global starting point. This category involves methods like fed-prox and some other algorithms. And second is that we can make corrections to the updates from each participant. And this category includes methods like a scaffold. And third one and a big category will be personalization, meaning that each client can have different models, and when server performs the aggregation, it may not produce only one global model. It can produce several, and maybe one for each client or one for a subset of the clients, so that the optimization process will effectively utilize the updates from each client. Yeah.
Okay, and the other question is basically say, hey, I've developed an advanced medical AI application capable of predicting outcomes and restructuring medical data in 3 dimensions. The question is whether this is kind of suited for cross-silo or cross-device or something in between.
I think for medical applications, mostly it is a cross-silo scenario because thinking usually is a collaboration between different hospitals, say. and clinical institutes. So usually, if we collect, say, tens or 20s such institutes, that will be a very big collaboration already. And and maybe for like medical devices at device level, the CT machine or surgical machines, that will be a little bit more than institution, but I will expect it won't be like cell phone or or wearables at that scale. So I would say that will be something in between.
Thank you. Please continue.
Okay, thanks. Thanks for the question. And for the security requirements, usually we have 3 states of the data: at rest, in transit, and in use. And models can be intermediate results that we want to protect specifically, or the model itself. And of course, we have different attack patterns to take care of. And in order to counter those secure attacks and to satisfy the security constraints, we can have security mechanisms like homomorphic encryption, differential privacy, or confidential computing. And those mechanisms can be injected to help us to satisfy the security restrictions. And of course, we have communication constraints from network bandwidth. Is it across globe, or is it local communications? We have constraints from information size. For example, large language models, the models themselves are very large. And of course, we also need to consider the latency, tolerance, and local computation power, and such that we really want to make our fundamental supporting platform robust across all those security mechanisms, and across all those communication constraints. We should expect a versatile communication pattern that can that can enable different communication topologies, and with easy access to different security mechanisms. And for the algorithms, I will quickly go through these parts. The very baseline will be fed averaging. And for deep learning applications, this is something very easy to understand, because what is being shared is just a set of weights. You can consider them as a dictionary. And how the server aggregates will be just the weighted average of different weight submissions. And what clients do with the global model is also simple, because it's just starting from the global model to continue with the local optimizations. But if we generalize to traditional machine learning algorithms, what averaging means will be a little bit different. For example, regression models, well, they are essentially the same as neural networks. They're just coefficients and intercepts. So those can be the same as deep learning models using the weighted average. But seeing methods like k-means clustering, it's gonna be average over the centuries and count statistics. And like nonlinear SVM, we will perform global SVM step as to average or aggregate the information collected from clients. And like tree methods, say XGBoost, there will not be a simple algorithms that can average the trees received from different parties into another single tree, but rather we could utilize bagging mechanism to bag all the local trees to form a forest. That is so as we can see, the average meaning will change depending on what particular machine learning algorithms you choose to solve your own data problem. And talking about research in federated learning domain, there are various research trying to handle challenges from different angles. For example, what are the motivations for people even to join a federated learning study? people usually expect same or better accuracy on local data than locally trained model. And of course, better generalizability than the locally trained model on unseen data. And hopefully, the eventual model will be comparable to centralized training if all data are shared together. And some other concerns from participants is the process of federated learning fair, or do we satisfy the security constraints? And of course, other challenges involve 9D distributions, estimate the fairness, and address the vertical settings. So this is one work we did last year about fair federated learning via client contribution estimation. The main goal is to estimate the collaboration fairness and performance fairness via this contribution Shapley value evaluation metric. We actually consider both in summation gradient space, whether one submission contains novel information as compared with others, or also in the data space, whether this resulting model helps to improve the local performance. So by combining these two factors, we show that the learning process can be more effective using this more sophisticated weighting scheme beyond the basic Fed averaging setting of using the number of samples from each client. And here is the second work we did last year. Is about communication efficient vertical federated learning. And why do we need communication efficient vertical federated learning? Keep in mind, in horizontal deep learning case, we do it epoch-wise. And the reason is that each epoch have too many optimization steps. And that will be a significant burden for communication. But once we move from horizontal federated learning to vertical federated learning, we can no longer have that luxury of performing sync every few epochs. Because for vertical federated learning, a round of training needs to perform across different client participants. So that is why in this case, the vertical federated learning, the process gonna be exactly the same as distributed learning. And that is why if we do it in a regular term without inventing some communication efficient mechanism, we will not be able to afford that. And in this work, we reduce the training process into one shot or few shots. And in order to do that, we perform semi-supervised learning and adapt the several mechanisms in order to enable such one shot or few shot learning, particularly for this vertical federated learning scenario. And yeah, lastly, I want to talk about our framework with FLIR to support the real-life studies. One message I want to deliver is that NVFLIR, as of today, is a realistic platform that can be fully utilized to perform real-life studies. It not just for research purpose, it's for real-life federated learning studies. And yeah, federated learning framework, we want it to be domain agnostic, whether it's healthcare or financial or monitoring, they can all utilize this framework to train a global model. And it can provide multiple layered security and data privacy mechanisms, including user identity check, including the communication security, and also the privacy preserving techniques. And we want to make it research friendly by inventing some easy to use APIs that you can easily adopt your local training scripts into a federated learning step, and it's applicable to real life scenarios by providing security, privacy mechanisms, and orchestration the whole federated learning process. And to help users to implement their own algorithms, here we provide several tutorials and different algorithms and research items I just talked about, like the FastCE work and the one-shot vertical federated learning algorithms I just talked about. Everything is in there. And also, of course, the traditional machine learning algorithms to help people understand how to formulate a particular algorithms into a federated learning scenario. And we, of course, provide other security features, including differential privacy, homomorphic encryption, and most recently, the confidential computing to secure the data in use and in training. So a summary for pfl is built for productivity, security, scalability, customization, and really it's for supporting the real-life federated learning study. And feel free to check out our GitHub and the documentations. And a few final words in the age of foundation models and large language models. Why federated learning is still relevant is because data cannot be centralized in many large language model or foundation model tasks. For example, the reports from different hospitals or financial data from different institutions, they have very high privacy and regulation constraints, and due to copyright issues, they cannot be shared. And in the meantime, the huge amount of data and is needed for training the foundation models. Like any other deep learning techniques, more data could help to achieve a better or more generalizable model, which is actually a must for being foundation. And federated learning provides various options, including federated training, and personalized models, and federated learning, inference, evaluation, and data corroboration. And what's more, we can say at the moment, federated learning can roughly categorize into cross-silo and cross-device, but the boundary between the two can be fuzzy with a growing computation power on edge devices. For example, Nvidia Holoscan for medical devices, it is equipped with Nvidia IGX, and it has a pretty decent GPU, the RTX A6000. And with the decent computation at edge, it will be less than cross-silo scenario if we think about the number of participants, but with a lot more realistic for robotic AI assistant devices. And thinking about why we need federated learning, in some scenarios, data recording and transmission will unlikely be affordable or even allowed. Such as operating room decisions, those data, how doctors perform the procedures, those data will never be recorded. So the only chance for us to learn anything from it will be just on site when doctors perform their procedures. And the training information in those cases, it can be real-time and sensitive. And for those applications, really, the federated learning will be our only option. And so in summary, in order for us to really perform federated learning for our own applications, we need to consider several challenges from data modalities, from data splits and data heterogeneities and security requirements. We want to pick the best algorithm to solve our data challenge. And finally, we need one framework that is effective for support real-life studies. And thank you. And if you have any questions, feel free to contact me.
Thank you, Ziyue. I think we have one question. So how does the Fed average handles the challenge of non-IID data across different clients? And could you explain how the aggregations models like XGBoost that relies on the sequence improvements and works in the federated learning environment?
Fed averaging actually does not specifically take data heterogeneity issue into consideration. The only mechanism for basic Fed averaging is the weights, which is simply the amount of data at different participants' level. And so, yeah, if we want to specifically tackle the challenge from data distributions, we need more sophisticated calculation mechanisms. And yeah, that's also true for if we think about other different machine learning algorithms like XGBoost. Basic averaging, of course, it will not counter that, but at least we can have some mechanisms to properly calibrate and calculate the weights between different participants, and hopefully that weight's gonna help us dynamically to achieve a better global model or better personalized model process.
Thank you, Ziyue, and